So today I'm going to start talking a little bit about search heuristics for mixed integer nonlinear optimization. And we're interested in search heuristics for two reasons. One, some real world problems you just cannot solve. And I have some problems where the solvers would run for 2 weeks to produce a solution. And that's just not good enough. And often it is perfectly acceptable in an engineering world to have a good solution rather than an optimal solution. So sometimes the problems are just too large, they have too many variables or too many integer variables, and they generate really massive search trees. And sometimes we have problems that we want to solve in real time. So for example, if you're driving a car and you're thinking about gear shifts, those are discrete decisions, and you need to make those as you're driving along if you want to drive a car as energy efficient as possible, for example, for self-driving cars. And I have colleagues who've worked on this with sort of Mercedes-Benz and other places in Germany. So heuristics are really ways of finding a feasible point quickly, but without any optimality guarantees. So it gives you an upper bound, a solution, a current solution that you could potentially implement. But they also help us with searching our branch and bound or branch and cut tree, because we identify good incumbent solutions quickly. They might help us prune parts of the tree that are dominated then by the upper bound. They can also help us guide to where good solutions, other good solutions might lie. So you could think that if you found a good solution, maybe there's other good solutions nearby. And those are, I'll talk about these heuristics as well. And it also allows us to do better bounds tightening for non-convex mixed integer nonlinear problems, because you now have an upper bound on the objective. And that means you can use that in the feasibility or optimality-based bound tightening techniques that we talked about yesterday. So all those techniques now mean that you can get tighter relaxations, for example. Okay, so the first question you should ask, and I put this here for you, so somebody should ask, why not simply round the solution? So here's a very simple heuristic, right? You solve the continuous relaxation. So I have my mixed integer nonlinear optimization problem here, and I replace the integrality conditions that y is an integer by the fact that y is a real now. And so if I do that, then this problem up here becomes a nonlinear optimization problem. And we can solve problems of this type probably with millions of unknowns in a reasonable amount of time. It depends on the structure, it depends a little bit on the solver, but you can go up to millions or even hundreds of millions of variables there sometimes. So then you have a solution y hat, and you simply round it. So if it's a binary variable, anything below a half you set to 0, anything above a half you set to 1. So what could possibly go wrong with this? This sounds like a really great and simple idea. And so first of all, when I round the integer variables, my axis may no longer be feasible. So in particular, if I have units that I put into a flow sheet, for example, in chemical engineering, and the integer, the continuous relaxation tells me to have a quarter unit somewhere, then there will be discrete variables associated with this unit, but they're no longer feasible. So in particular, if I have constraints of the form that we've seen, where I have some continuous variables that are bounded above by a binary variable and some upper bound. And so now if y is a quarter, then xi can be positive, but the rounding of y is 0, and that means xi must be 0. And so I could maybe fix this up afterwards, but there's other things that could go wrong as well. And there's the rounding also ignores the objective, but most importantly, there's some simple examples for integer linear optimization which show that rounding can be arbitrarily bad. So it can be as bad as you could possibly make it. So I'm going to draw the feasible set of an integer linear optimization problem where I have an integer lattice over which I'm optimizing, indicated by the red dots. And now I'm going to add just a simple set of linear constraints, and I can make them sort of, this is one of my linear constraints, so I have to lie below this line. And the other linear constraint is going to be almost parallel to that. I'm going to make it like this. And now assume that my objective is pushing me into this direction. So this is minus the gradient of f. And so my solution, the relaxation, would lie here. This is the point. Y prime is the relaxation. And rounding it, you have 4 choices, right? And any of those 4 choices violates these constraints. In fact, you have to go a long way back before you find a feasible point. So, you know, to find a feasible point, they're probably going to be down here somewhere before you find a feasible integer. Oops. And so this is a well-known phenomenon that when you're rounding, you may suddenly violate a lot of constraints. This is a cooked up example, but you can make this arbitrarily bad by just making this angle very, very small. There are heuristics for mixed integer nonlinear optimization, and there's a class of heuristics called probabilistic methods, and you've probably heard of some of these. I'm not going to cover them in this class, but I wanted to at least tell you that these exist and you could use them. So there's simulated annealing, which is probably the first of these heuristics, which is motivated by the physical process of simulating the cooling of metals, for example. And the idea there is that you're doing a descent algorithm, but you have some probability of escaping local minimizers. And simulated annealing is actually the basis for quantum annealers, such as D-Wave. The D-Wave machine is a big machine that implements simulated annealing, basically for quadratic optimization problems over the integers. There's taboo search. Genetic algorithm is very popular. So there you start off, I got this image from the internet, so internet very useful for creating cool images. So you create a number of random specimens, so those would be random solutions that you selected, integer feasible solutions maybe. You find the best of them, and then you create new ones out of the best ones by either crossing them or permuting them in some way. And so permuting and crossing them means you're combining the integer variables, you mutate it to some randomly, and you repeat. You go around this genetic algorithm loop. And there's variants of it that have various names, such as particle swarm and ant colony optimization, that are very much in the same flavor. They're all inspired by biology. They try to mimic what biology is doing. And the cool thing is they're very easy to understand conceptually. They're harder to analyze, and they don't have any rigorous convergence proofs unless you assume you have an infinite amount of time. So instead, I want to concentrate on deterministic methods that also go better with our deterministic mixed integer nonlinear solvers. So the simplest heuristic is to just run an algorithm for a fixed time limit or node limit. So you could just take your branch and cut algorithm and as a heuristic run it for a limited amount of time, and that solution, and if it generates a solution, that is a heuristic solution because you haven't run it to completion. And then there are 2 classes of heuristics that we'll talk about here. The first one is search heuristics, and they're able to find a solution without any known prior solutions. So you don't need to give it a solution. They will somehow search in a clever way and find a solution for you. And the search heuristics are different to branch and cut in the sense that they don't have to be rigorous, so there's much less overhead. They're trying to be much more efficient and cheaper and use cheaper constructs. And then there are improvement heuristics. So those are heuristics where I have an integer solution and I'm looking for maybe a nearby integer solution or something that looks, a nearby solution that is better. So there I'm assuming that if I have scheduled, I do scheduling of delivery and I've maybe scheduled the first 3 days optimally, then the solution to scheduling 4 days would probably be the 3-day schedule plus something that I changed on the 4th day. Or that might be a very good solution. And some of these heuristics you can actually make into complete algorithms, which means that they will be convergent and rigorous and give you the global solution to your mixed integer nonlinear optimization problem. But then they require more time and more effort. Okay. And all of these heuristics may include some random elements, but I'm not going to talk too much about this. So the search heuristics, for example, might have some randomness into which trees they search or how they search the tree. There's also now some research being done into randomized methods for discrete optimization. And so you may have heard of randomized methods for linear algebra that sort of exploit the fact that certain problems lend themselves to doing randomized projections and working in subspaces. And those randomized methods are also now becoming popular in optimization. Okay, so we're going to solve these problems in a heuristic way, and there's some terminology that I want to sort of use for this and the next 2 slides and lectures. And so I'll remind you of what these things are, but I'm going to use a star or X star, Y star to indicate the current incumbent. So that's a point that is feasible. That's my current best solution, my current best guess. And if I had to terminate now and give you a solution, that would be the solution that I would give you. And I will denote by this dash a local solution of a continuous relaxation of my mixed integer nonlinear optimization problem. And then whenever you see the diamond at the top here, that's supposed to indicate that it's a solution of a polyhedral relaxation. So for example, if I take my mixed integer nonlinear optimization problem and I introduce my outer approximation cuts and replace my constraints, my nonlinear constraints and my nonlinear objective by these outer approximation cuts, then the solution to that problem, or a solution to that problem, will be indicated by these sort of diamonds. And so the little diamond shape means polyhedral, right? It is a little, that thing up there is a little polyhedron. So that's what that seems to indicate. Okay. And so then, just as a reminder, we have at our disposal various problems that we can solve, or we can solve approximately, in order to put a heuristic together. And so one of the problems that plays an important role is this outer approximation master problem. And so assume that I'm being given a set of points P at which I have linearized my objective and my constraints. So X hat, Y hat are points that live in this set P of finite points that I've visited before, and then I have these linearizations that are available. And so this is the standard outer approximation master problem, or outer approximation mixed integer linear optimization problem. Okay, so here's another example of how rounding could go wrong and does go wrong. And this is kind of, again, it's cooked up. I think most solvers deal with this in a rigorous way now. But here I have a special ordered set of type 1. So I have a set of P binary variables, xi, such that their sum is equal to 1. So this is, we also call this the one-hot encoding. So it's encoding, for example, a choice of diameter if I design my pipe network, or a choice of action that I can take at a certain point. So it could, for example, also encode the choice of a gear that you use in your car. So you could use this to encode the gear change sequence in your car. And then when you solve a relaxation, unfortunately what happens is that most of the time, if you solve a continuous relaxation, it will just smear out these xi's. So it will almost equidistribute the xi's, this 1 over all of the xi's. So I have p of them, and so what you see in many applications is that the continuous relaxations is just 1 over p. Right? If I put 1 over p in here, sum it up p times, I get back to 1. And the reason for that is that it's sort of best to somehow keep all options open. So if I have a whole bunch of these binary variables that I have over here, then the best choice is often to have all of them open and operating. And so one remedy is a technique that was developed by Pietro and a colleague of him, Giacomo Nannicini. And so they developed this technique in the context of binary mixed integer nonlinear optimization. So that's a very important class of subproblems. I can also always take any integer optimization problem where the integers are bounded and rewrite it as a binary optimization problem by using the one-hot encoding, for example, of the integer variables. But you could also do this, I think you can also generalize this to having general integer variables. There's really no loss of generality here. But just to make it easier, we assume that we can solve a relaxation. So we solve the continuous relaxation, maybe locally, if it's a global optimization problem with non-convex constraints and a non-convex objective. We have a solution to the relaxation. And then we set up this problem where we're looking at a proximity objective or L1 distance norm to this relaxation that we computed here. So this is a continuous value. The yi prime is a continuous value that we computed. It's the solution of my relaxation. So that could be this value up there, for example. That would be my y prime. And I'm now looking for a point that lies inside this first linearization that I can set up. So the first outer approximation that also satisfies the integrality conditions. And so in this case, if I did this over here, the closest point that I could find to this point up there is probably this point here. So that's probably the closest point. And the nice thing is that if I do this in the linear case, then I'm guaranteed that I now satisfy my linear constraints. So the nice thing is if I go back to the previous example, I would not, the rounding if I rounded this problem, then I would get all zeros. I would violate my one-hot encoding constraint. But if I do it this other way, then I would find a solution that actually satisfies this one-hot encoding constraint. And so that's very nice. And you can put this into an algorithm, so you can now update these sets until you find a good solution. So in particular, if I only have linearizations of my nonlinear constraints, then they may not be infeasible. And so I can now go around this loop where I set up these relaxations. Initially, it's the mixed integer linear optimization relaxation, but I'm going to add cuts to it later on. And then as long as I haven't found a feasible point, I will resolve this relaxation. I will find a local solution in which, for the nonlinear optimization problem, where I fix the binary variables. So I get a, oops, there should be an x here. Let me just correct this on my slides here. Sorry, it should be a y, not an x. So I'll correct that. The second component here should be a y. So I get out a solution of the relaxation. That's an integer solution. And I take that and I now solve the nonlinear optimization problem where I fixed those binary variables. And then I'm going to add a cut to my relaxation that basically excludes this point from further consideration. So this cut is a cut for over all the integers. And it basically says that the distance between any future point that I take and this solution that I just generated has to be at least 1. The Hamming distance has to be at least 1. So that means I cannot put the current point back in there. So if I added yi diamond here, then the distance would be 0. All these absolute values would be 0. So that violates it. And that's also the only constraint that violates it. So if you put any other integer assignment in there, it will satisfy this constraint. Right? And what you're counting is just the difference in zeros and ones between two integer variables. So if I have one integer solution, y dagger, which is 1, 0, 0, 1, 1, and any other one that just differs in one digit from this would be feasible. So 0, 0, 0, 1, 1 would be okay, and you can just check that all other ones satisfy this constraint. So this is called a no-good cut, and it just eliminates the one integer assignment. And so it means that while I'm looping around, I'm looking for integer solutions that lie close to my relaxation, that satisfy some loose outer approximation. I'm not refining this outer approximation of my feasible set. And as soon as I find one where this x prime is also feasible, then I will stop. Okay, so I stop when I find a feasible solution or when this relaxation becomes infeasible. And it becomes infeasible because I've added too many of these no-good cuts. So I've now excluded potentially all integer assignments. Okay, so some properties of this method. It automatically satisfies the combinatorial constraints. So any constraints that you have on your integer variables, your binary variables, the combinatorial structure will always be satisfied. And that's really nice because it means that the integer that you're generating is one that kind of makes sense from a combinatorial point of view. The only thing it doesn't satisfy are the nonlinear constraints, and so you're now testing a sequence of integer feasible solutions to see whether they also satisfy the nonlinear constraints. And as soon as they do, you're done. You have your initial assignment. And so it terminates. There's two possible outcomes. One is that you find a feasible solution, and that's great. You found your potential incumbent that you can now use to prune other parts of the node you can use in your branch and bound throws. Or it terminates by saying this problem is infeasible. And so then you can, under certain conditions, you can say that there are no integer feasible points. But it is really quite expensive as a heuristic because it's, if you go back to it, what you're doing on each iteration is you're solving a mixed integer linear approximation, the relaxation here, and then the nonlinear optimization problem. So that's exactly the same cost like outer approximation. The problems are maybe a little bit simpler to solve, but it is essentially the same cost. And so that's something to always bear in mind. And that goes back to the point that I said earlier, where I said, well, one heuristic is always just to run another algorithm. So that's always a good heuristic. And most methods, such as BonMin or Minotaur, actually have more than one algorithm that you can try. So a good heuristic is run each of these algorithms for a few minutes and see what happens. Okay, and then I'll talk a little bit about diving heuristics. These are also very simple heuristics. And again, they're mostly heuristics. Some of these heuristics were developed for mixed integer linear optimization, and they're very easy to generalize to mixed integer nonlinear optimization. There's not much technology that goes into it. So the basic idea is do a very quick depth-first exploration. And so the idea is that you, again, start by solving a nonlinear optimization relaxation, and then you fix some of the integer variables, either to the lower bound or the lower rounding or the upper rounding. So you can either set it to the floor or the ceiling and resolve this nonlinear optimization problem. So what you're doing is if you think of this in a branch and bound search, you solve your relaxation and you get x prime, y prime. And now I can pick a whole bunch of variables y prime, and I sort of said yi prime is either I set it to the floor of, I set it either to the floor of yi prime or to the ceiling of yi prime for some I in the integer set of integer indices. And so when I do that, I sort of skip over a bunch of levels in my branch and boundary. I sort of tunnel through this, and I get it to a new problem. So rather than doing a rigorous branch and bound, where you now have nodes and you branch on each variable individually, you just skip over those. And now you have a new nonlinear problem that you're solving, you get a new relaxation, and you repeat. And so what Pierre Bonamy suggested is to dive on the smallest fractional value. So you look for the value of the integers whose fractional part is the smallest, or the one that's closest to the integer. There's another one that also looks at small objective gradients, and there's some heuristics. So you can have various ideas maybe on how to do this. One of the issues is that this again ignores potentially the special ordered set type 1 structure. So in this case, we saw this earlier, the relaxation that you would get is probably one where the yi's are all 1 divided by p. So if p is a large number, then those are the ones that you would set all of them to 0, or too many of them to 0. So this might not be a good thing to do. Instead, what you should do when you branch on a special ordered set is actually compute the center of the set. So the set is used to model another variable which is discrete, which has, for example, discrete diameters, and you can compute the center or the average weighted sum of these variables here, and then find the branching point that corresponds to where you lie exactly between two of those consecutive ones. And we've looked at this. This is special ordered set branching. You can just do this, and if you implement this, then you're sort of branching on this disjunction. So you're setting a whole bunch of binary variables either to 0 or to 1. And this can be implemented, and so I had a student a few years ago implement this in Minotaur over the summer. And if you do the sort of standard, simple way of doing the bounding, then your objective function that you get, the objective function of the solution that you generate in the heuristic is much larger than the objective function that you get if you do this in a different way. And you can detect other structures. So there's a sort of simple way of extending what these guys proposed by simply looking at other ways of how you decide either how to do the branching or the fixing in this case. So in this case, we're fixing variables in a different way, and we're just using techniques from mixed integer linear optimization. There's absolutely nothing new here. This is just very, very simple. But simple ideas often have a big impact. So there's sort of some nice results there. Okay, so heuristics are very important, and I'll talk more about this in the next 2 lectures. They create feasible solutions quickly and help us with bound tightening and pruning nodes in the branch and cut tree. So they're very important for the process. We don't just run these heuristics at the root node of the branch and bound tree. That's one option, but we can run them at various other nodes in the branch and bound tree. And part of designing good heuristics is to make sure that you can run them quickly and efficiently in many parts of your branch and bound tree. But you have to be aware that if you run them in a subtree, then whatever conclusions you come to may only be valid in that subtree. Simple rounding doesn't work. You probably knew this. There's this example up there that shows you that you can be arbitrarily far from a feasible point if you do simple rounding. And a lot of the heuristics for mixed integer linear optimization can be directly translated to mixed integer nonlinear optimization. And so not all of them have been translated yet. Some yes, some no. So there's still things that one can do there. And I showed you one of those diving heuristics that exploits a little bit more structure than the standard diving heuristic.